Yeah, okay. Okay, amazing. Okay, so welcome everybody to the next installment of our weekly reading group. I'm really excited today to welcome Professor Chris Kachris. He's an assistant professor in the Department of Electrical and Electronics Engineering at the University of West Attica, where he's been since November 2023. He's the co-author of more than 90 peer-reviewed publications in the domain of reconfigurable computing and hardware accelerations, and his work has been cited in more than 2,665 papers. So we're really, really excited to welcome Chris with us today, where he'll be going through his review on hardware for LLMs. So yeah, the floor is yours, Chris. Welcome, welcome.
Thank you very much, Daniel. Can you hear me?
Yes, we can hear you. Yeah.
Okay, great. And I guess you can see my screen, right?
Yes.
Okay. So today I'm going to talk about a survey that I did on hardware accelerators for large language models. So probably you know better than me how important large language models are, and in general deep learning. So, and it seems that it is one of the hottest topics right now, the large language models. And that's why there is a lot of research effort on how you can accelerate large language models, because it's very computational heavy, right? In this presentation, I'm going to give first a short introduction about the available options when you want to accelerate an algorithm or an application. And then I'm going to discuss available options, the proposed solution, and I'm going to present one representative paper in each category, right? So first, let me give a very short introduction about the available computing platforms. So the basic one, the most obvious one, is the CPU, right? So the CPU has the main advantage of the CPU is its flexibility. You can write any program in any programming language, Python, TensorFlow, Java, C++, right? Whatever programming language or framework you want, and you can very easily run it and very fast, right? You just need to compile it. It will take a few seconds, and then you can run it, right? So this is the most obvious solution. And then we have the GPUs. GPUs, you can think of it like a more it's a many-core processing element. It has multiple computing elements and multiple processing elements, but each processing element, it's much simpler compared to the CPU. It's not so much complex. It doesn't have a branch prediction and several other functionalities that typical CPUs have, but you have the advantage that you have much more processing elements inside the same chip. So especially in applications like image processing and video processing, etc., you can process several of these data in parallel. And then we have some specialized chips. It can be AI chips, or it can be specialized ASIC, application-specific integrated circuit. In the past, we used to have an ASIC, an application-specific integrated circuit, for network processor, for communication, for DSPs, etc. And now there are a lot of companies that they provide specialized ASIC just for AI application and deep learning applications. And then you have the FPGAs, in which I will elaborate more. You can think of it a very, let's say, naive classification is that the scalar architecture is usually, the CPU are scalar architecture, meaning that they are very fast on scalar kind of application. You have the GPUs that they are very fast on vector or matrix multiplication. Then you have AI that they are very efficient on matrix multiplication. And FPGAs can be also support a tensor kind of application, right? So, for example, just to give you an example, Intel is one of these companies that try to provide one solution for each kind of computing architecture, right? It has the typical Intel CPUs. It has GPUs as a vector processing unit. It has very recently, last year or 2 years ago, they acquired Habana Labs, and before that, Nirvana, I think, that they are specialized on AI applications. And in 2016, they also acquired Altera Technologies, that it was one of the 2, 3 major vendors, FPGA vendors, in order to also provide application about FPGAs. Now, the main advantage right, of the FPGAs, ASIC, and GPUs is how they can provide better performance compared to the CPUs. Right, so just a very short introduction. When you have a CPU, first you need to feed the CPU with the instruction memory, and then you need to feed the instruction memory tells the CPU, okay, now I have to do a multiplication. Then the CPU has to fetch the data from the data memory, and then it will start doing the multiplication, right? In the domain of FPGAs, or in general, the ASIC, things are a little bit different. FPGAs, for example, consist of some basic elements that it has that can be used to do operation like AND or addition, multiplication, etc. And then you can have an array of this basic block that you can connect it through some interconnection network. Now, the main advantage of the FPGAs is that you don't have to limit your architecture into a specific, let's say, 6-bit adders or 32-bit adders or multipliers, or even a 64-bit, right? So when you want to do, let's say, an 8-bit addition in a CPU, you have to use the 64-bit ALU architecture that it is typical in an Intel or an AMD processor, right? So even if you want to do a very simple addition, an 8-bit addition or 8-bit multiplication, you need to use the 64-bit architecture. In some cases, that has significant overhead, right? The main advantage of the FPGAs is that you can develop your own custom architecture using basic elements, and I will give more details on how this can be utilized in the domain of large language models. So as you see in the typical CPU architecture, you have to fetch the instruction from the instruction memory, you have to decode it, then you have to instruct the register file, which register do you want to use, then you want to feed into the ALU and do all this processing. So this one takes a lot of time, and of course it takes a lot of energy, right? So in the domain of FPGAs or application-specific integrated circuit, you kind of hardwire all the instructions into the FPGA, into the circuits, so you don't need any more to fetch the instruction because the instructions are hardwired into the circuit, are hardwired into the FPGA. So instead of doing all this transfer of data from the data memory back to the register file, from the register file to ALU, etc., when you design a custom architecture for FPGAs or for an ASIC, you have the advantage that is a data flow architecture, meaning that you provide the data will go to the first multiplier, then they will go to the second multiplier, and then they will be stored into the memory, right? So you save a lot of time, you save also a lot of energy, right? So here is a typical architecture, right? If you have an FPGA or an ASIC, and you have some A, B, C, D that are the data, you just add this data, and they will follow this data flow architecture that you don't need any more the instruction memory, you don't need anything else, right? And on top of that, you can think also the GPUs and the FPGAs have now they have also specialized units, the tensor cores that enable AI acceleration, right? So in the past, the FPGAs and the GPUs were mostly basic building blocks. In the case of GPU, processing elements for image processing. In the case of FPGAs, different kind of building blocks for logic, for digital logic. But now you have specialized tensor blocks that are specifically designed to do very fast functions like matrix multiplication, right? And in the case of the FPGAs, you have also the soft logic that allows you to do other kind of processing, like I will show you later, like in the case if you want to do some normalization, if you want to do some Gaussian softmax, the addition, accumulation, etc., that it is typical in the case of large language model, right? So in the case of the FPGAs, you have also smaller building blocks, memory building blocks that you can allocate very close to the processing elements. So that way you save a lot of energy because you don't have to transfer data from large memories, in the case of the GPUs, right, to the processing core. You can have several distributed memory blocks close to the AI tensor block that allows you very fast to transfer the data from the memory to the compute units back to the memory, etc. Right, so this can be utilized in several applications. Just let me give you one simple example about the AI tensor block. In the past, the FPGAs, they used to have these DSP blocks, digital signal processing block, because FPGAs were widely used in communication that required a lot of DSP logic. So, and they can be used to do some 60-bit multiplication, accumulation, etc. So in the case of FPGAs, Intel, for example, has developed this AI cores that they are specialized for application like deep learning, machine learning, and LLMs, because they have a dense arrays of lower precision multipliers that is typically used for AI application. And then the smaller multipliers can be also aggregated to construct large precision multipliers, right? So you can see on the left figure that you have a lot of registers, you have a lot of multipliers that can be later fed into this accumulator that does the accumulation. You have also the converter from fixed point to floating point, etc. You can do also some addition, etc. And it is very efficient because not only you get a lot of performance, but it is also very energy efficient because you don't have anymore to do all of this instruction fetch, decode the instruction, load the data from the register file, etc. As I discussed, right? So there are several advantages. And besides the GPUs and FPGAs, you have also a very novel architecture that it is called in-memory computing, that in that case, you take advantage of analog computing, kind of, right? So in this case, the matrix vector multiplication is done using resistive crossbar. And the idea is that you have, you activate simultaneously the voltage across these word lines. You have some digital to analog converter. You convert your data to analog signal, and then you can have this analog signal traverse this resistive crossbar. And the advantage is that the currents from multiple in this column will be automatically accumulated because of Kirchhoff's law, right? What we know about electric signals and electrical circuits. So in that case, you take advantage of the Kirchhoff laws of how electrical circuits work in order to do the matrix multiplication. And then once you have the analog signal, you convert it back to a digital signal. Right? So let me go now in the large language model. So the main idea when you want to accelerate a large language model is to identify what are the most computational intensive functions of these algorithms, and then you try to accelerate this function, right? So you have to start with the basic building blocks, right? That consist of the encoders and the decoders, and you have to identify what it is the most computational intensive part. Is this multi-head attention? Is this the feed forward, the linear, the softmax, the rectified linear units, etc.? And then you try to accelerate maybe all of them, maybe most of them, etc., depending on your proposed architecture, right? So what we did was trying to find the most novel solution for each category. So I tried to identify what are the basic, the most promising solution if you try to accelerate large language model. And I did this survey that you can find is available on GitHub and on ArchiveX. So what I'm going to do is I'm going to give one representative, I'm going to present very fast one paper from each category, right? So the main idea is that I just provide the framework. I cite also the technology, which technology has been used, in this case, the FPGA, where it is available. I also present the speed up for its proposed solution, the energy efficiency, if there is. In some papers, they also do the energy comparison. In some other cases, it is not available. And of course, the very important thing is that the baseline, what do you compare with, right? You can see, for example, in some cases, they compare with an ARM processor. In some cases, they compare with a state-of-the-art GPU, V100 GPU, right? In some other cases, they compare with against CPU. And again, it's very important if you compare against a single thread implementation or if you compare against a multi-thread implementation, right? So in this case, transformers is compared, the FPGA implementation is compared against an 80-thread implementation, while in some other cases, it may be compared against a single thread implementation, right? So it's hard to do a fair comparison, right? So I will start with FPGAs, and I will start one of this paper. I think it is the one of the latest, the one that was presented 2020, but it is very representative about FPGAs, the FTrans, the energy efficient acceleration of transformers. And the main idea in this case is that you have the host processor and you have the FPGA. The FPGA, it has the main disadvantage is that usually it cannot work standalone, but you need to have a host processor, right? So another CPU that will be used to feed the data, etc. So in this case, we have the host processor, the CPU, that it has the memory, and it transfers the data through a PCI Express interface. So the FPGA card is hosted into the PCI Express, and then it sends data to the DDR memory of the FPGA, and then from the FPGA, you try to do the acceleration of the task, right? The acceleration of the functions, right? So in this case, you have this is the main building block. You have the encoder, and then you have the decoder. So this is the basic architecture for every kind of FPGA kind of acceleration. You have the host processor, you have the FPGA usually connected through PCI Express, and you offload the host processor in order to accelerate the data and the application to the FPGA. Now, there are several advantages in the case of the FTrans. First of all, they use some dot product attention since it is much faster. They also use some model compression that leads to reduced weight storage because they replace the original weight matrix with one of circular matrix. And then they have some Fourier transformation that I will present. And of course, they try to offload the dedicator to off-chip memory. So the first thing is that they selected the dot product attention as it is much faster and more space efficient. And then they have implemented a multi-head attention using by concatenated multi-single head attention, right? So the main idea is you try to take each of these building blocks and you try to do some very good implementation of how this will be translated to hardware. Right. So in the case of F-trans, they developed this multi-head attention that it has several processing elements, and each one is a single head attention function, and they try to accumulate all of this. So the main advantage is that they exploit this parallelization because they have multiple building blocks. Now, the second advantage is that instead of doing directly performing the matrix vector multiplication, F-trans, they use the fast Fourier transformation because it is much faster. It's very efficient to do it also in FPGA, right? So they first translate it to fast Fourier transformation. They do the multiplication, and then they go back to the original arithmetic, right? So this is one way to take advantage of several cases. Another solution, as I said in the beginning, is to use the GPUs. Right. So in that case, of course, we all know that GPUs are used for the training of large language model. Especially one of these reasons is that GPUs are very much efficient, especially when it has to do with floating point operation. But in some cases also it makes sense to use GPUs also for the inference part when you don't have so much floating point operation, but you need to do a lot of operation in parallel. So in many cases, you will see that there are several methods on how you can use GPUs in order to speed up large language model. And a representative example in this case is light sequence 2, that it has some layer-specific kernels that they want to increase, that they can be used to increase the GPU utilization. And on top of that, they use some fine-grained mixed precision trainer. So they do some batch updates on reduced precision parameters rather than having many individual updates. And of course, they try to do some efficient memory management, GPU memory management. So let's take it step by step. Right. The first one is this. They fuse the kernel operators for both the encoder and the decoder. And the main advantage is that instead of having many fine-grained elements, they fuse it into quartz-grained kernels. What is the main advantage? So usually when you want to design something, we all know that the best approach is to have smaller functions and to call all of these functions. So a modular approach when you try to design a complex system. It happens, however, if you have multiple functions, every time that you call a function, you need to store the data, right? So you need to fetch the instruction, you need to fetch the arguments, you need to stop the execution, the main execution, you need to fetch the arguments, do some processing, then to put back the data to the stack, right? So it goes back to the operating system, etc. So if you have a lot of functions and you have a lot of kernels invoking lances, it may be slow at the end, right? So what they did here, the researchers, is that they replaced and they wrote some of these functions in order to have, instead of having a lot of fine-grained functions, they prefer to have some coarse-grained kernels that it will result in fewer kernel lances, and this will result in much faster execution, right? So instead of using the typical libraries from CUDA, right, the CUDA Plus or the GEM, the General Matrix Multiplication, they decided to develop their own custom kernels, right? This is the first approach. The second approach is that they merge also the computation of the context of presentation. Again, the main reason was to reduce the length of kernels and improve the concurrence. So instead of having a lot of cross-attention building blocks here, they prefer to have here one multiplier and one adder here, and just feed it with the data, right? So in that case, again, you save a lot of time because you don't have it each time to invoke the function again and again, right? And the last thing is that they also try to eliminate a lot of copies because it takes a lot of time if you want to do some memory copies, etc. So they try to eliminate the floating point copies of parameter and directly update the workspace with on-the-fly conversation, that it is also very efficient, right? And the main advantage with these approaches is that they manage to get around 3x speed up against the state-of-the-art GPU A100 implementation, right? So please note that this is it's much better if you try to do a 3x speed up against state-of-the-art than trying to have, let's say, I don't know, 10x speed up against a very naive CPU implementation, right? So it makes sense. It is very important what is your baseline, what it is that you compare with. Now, there is also this option in the domain of ASIC. An ASIC is an application-specific integrated circuit, right? So in that case, you develop a very custom architecture for the proposed architecture that you have in mind. And compared to FPGAs, you don't have anymore to have this interconnection network that because the FPGAs have this interconnection network because they can be reconfigured on the fly to do some different operation, right? In the domain of an ASIC, you don't have this interconnection network to connect the building blocks because you have a specialized architecture, right? Of course, the main disadvantage of this approach is that let's say the initial cost in order to develop an ASIC can be very high, right? It can cost you 2, 3 million, 5 million to develop an ASIC, right? Just to the NRU cost, non-recurrent engineer NRE cost, non-recurring engineering cost, because it takes a lot of time to create the masks, to design the ASIC, etc. Right? But it is very efficient, right? So especially in the domain of energy, it can be very, very much energy efficient. It can be 3 times, some people claim, or so 4 times, for 10,000 much more energy efficient compared with the CPUs and GPUs, right? So let me describe or present one of these, this Energon paper that propose a mixed precision multi-round filtering. And the main advantage is that they have some low bit width operation in each filtering round, and then they only they decide to do a high precision tensor processing only on the final selected pairs. And they also propose this coprocessor architecture. In this paper, they also present this, they do some profiling, and as you can see here, it is the attention mechanism that can go up to 70% on average in the total execution time. So the attention mechanism can, it seems to be one of the most computational intensive parts, so that's why they try to accelerate the attention functions and not so much the rest, the normalization and the rest of the functions, right? So how they do it is that they decompose the attention unit into a filtering unit and an attention unit. So the filtering units performs multi-round mixed precision filtering to select the important keys for each query. So the novel thing about this approach is that they select to do very low bandwidth selection. It's very low bit um, matrix multiplication, so it can be done very fast. And once they have done this low bit width multiplication, they can identify what are the most promising elements of this matrix that make sense to select it for this attention mechanism, right? So they do this low precision filtering matrix multiplication, and once they decide that okay, are the most important elements, then they try to do the high precision matrix multiplication for the sparse attention, and they identify which element makes sense to go to the attention unit. So this has the advantage that low precision matrix multiplication can be done much faster compared to high precision matrix multiplication. So they have this advantage, and of course, it's much more energy efficient. Right? And on top of that, they have to do this mixed precision processing that reduces the computation complexity, and then they do some they reduce these results, right? So in one clock cycle they can do this. You can see here that it is 2-bit or a 4-bit matrix multiplication, and at the final stage they have some 14-bit results, and then these 14-bit results they can be fed into this high precision matrix multiplication. Right? So as you can see here, they have several advantages. So both in the domain of throughput and energy. So they compare it against, of course, and not they compare it both for edge application and for server application, right? In the domain of edge computing, they compare it against ARM processor and an NVIDIA TX2 GPU, right? And they get significant throughput speed up. And they also compare it against a Xeon and a V100 server, right? Again, in several tasks, they have several tasks that they try to do some profiling. And of course, you get a lot speed up using this approach. And of course, you gain also a lot in the domain of energy efficiency. You can see here that it is orders of magnitude better, especially if you compare it with against the Xeon and the V100 implementation. Again, the main approach is that you don't have a standalone ASIC. Of course, you need a CPU because the CPU is the one that will provide the data. It will have the data coming from the network or data coming from the programming framework, etc. But the main idea is that you have a coprocessor. You have the host processor, and part of the chip is used in order to develop this architecture, right? In order to have this architecture. Right. And of course, it is important to note that the results out of this one is based on simulations, meaning that they have developed this architecture at the register level, at the gate level, and based on several tools, they try to do some estimation of how much would be the energy consumption, how much would be the performance, etc., based on, let's say, cycle accurate simulations and based on very gate level simulation, right? If somebody wants to test it in real time and wants to implement it, they have to allocate 3-4 millions to make the chip, right? I think $3 or $4 million to fabricate the chip and measure it in reality. And then we have this in-memory architectures, right? The in-memory architecture is very novel, but again, as in the case of an ASIC, it's not very easy to fabricate and have it in real time. You need a lot of high budget to fabricate this in-memory chips, and it's not so easy as it is in the CMOS technology. So it is a little bit more exotic technology. So I don't know how mature it is, but it's not as mature as it is the CMOS technology. And of course, in this case, you get, of course, a lot of speed up and a lot of energy efficiency. just to give you an example about this X-former, that it is in-memory transformers, the main advantage is that they use both non-volatile memory for the to process some elements and some CMOS technology, the typical technology that it is used for chips, in order to do some other processing. So specifically, they use non-volatile memory in order to do some static matrix multiplication when you need to multiply some inputs with static weights, with weights that don't change over time. And then they use a CMOS architecture when they have to do some matrix multiplication between the query, the key, and the value that keeps changing and it is not constant, right? So for this case, for the projection engine, they use this non-volatile memory in which the matrix multiplication is much more energy efficient using this memory store architecture, this in-memory computing elements, right? And as you can see here, the speed up that they can get up to 14x speed up, and of course they can reduce significantly the energy consumption. Right, so I uploaded all of these papers that I have checked in this GitHub that is available here in the GitHub Kachris survey. You can check it here, and of course, if you have any more papers that you think it is have to be included, yeah, feel free to send me the papers, and I will include it also in the survey and into the table. And I was trying to do some classification of these proposals. Right? So here in the y-axis, I have the energy efficiency when it is available, and on the x-axis, I have the speed up. Right? And it seems that the ASIC, they provide the best energy efficiency and a very good speed up. Right? And besides the ASIC, the in-memory architectures also seem to provide very good trade-off in terms of the energy efficiency and speed up. Right? Of course, as I told you, the ASIC and the in-memory architecture is the results are based on simulation, and you cannot have it, after one day, right? You even if you decide to fabricate, it will take you 6 months or 7 months to get back the chip, integrated with the rest of the components, etc. Right? While in the case of FPGAs and GPUs, you have the advantage that you can program it on the same day, and you can deploy it on the cloud, on the data center, etc. Right? And some notes that I would like to discuss, right, is that first of all, that every proposed architecture is compared against a different baseline, right? Some papers compared with a GPU's V100, some other with a GPU A100, some other with older GPUs, some other the baseline is a CPU. And of course, in some implementation are based on a single thread implementation, some other on multi-thread implementation, etc. So it is hard to make a fair comparison, right? So it's not very easy. Yes, you can make some general assumptions and general recommendation about which one is better, but it is of course hard to tell which one is better if you compare it with a different baseline, right? So this is one thing. And the second thing is that, of course, a lot of implementation, the baseline was on single thread. So it makes sense always to compare it with a state-of-the-art multi-thread implementation, because if you want to make a fair comparison, right? So ideally, you want to have a very good implementation in a GPU, state-of-the-art GPU, and then to try to make a fair comparison against GPU, right? So that's all on my side. So as I told you, I will try to, as long as I discover some new papers in this domain, I will try to add them into this survey, and I will keep updating the tables and this figure. So we have the basic architecture. But the main idea is that if somebody is interested to do some research in this domain, I will try to have all of these papers into one GitHub repository. So if somebody wants to have to get started on this one, it will have a single point of contact. It will have a single point here to try to find all of this hardware accelerated large language model, and I hope they will try to have some new ideas on how to further speed up large language models.
Amazing. We'll definitely engage in the GitHub repository. Okay, well, we should all, first of all, yeah, thank you so much. Let's give a round of applause, everybody, for Chris's great presentation. So I guess, I mean, I certainly have a few questions, but maybe first of all, anybody else have any questions? If so, feel free to raise the hand and we can go through anyone else has. No, okay, I'll kick off then. Quite open-ended. I guess, like, despite there being so many bespoke ASICs that are good for LLMs, the majority of LLMs are deployed on general GPUs and A100s and so on, and the vast majority, even when it's not an A100, it's a Gaudi or it's an Intel hardware or something that's, I don't know, more of a general processing unit, graphical processing unit than it is kind of a really LLM specific ASIC or something. I guess, like, why do you not think, I know there are some startups getting pretty well funded now that are building LLM specific ASICs and stuff, but why is the majority of this still going through very general architectures instead of specific ones? Is it because the economies of scale has been that the general architectures are still just what's out there in the market? Like, what's your thoughts on this?
Yeah, very good question, right, Daniel? Thanks. So I guess it is similar to what happened in the past with deep learning framework, etc. Right. So, for example, companies, especially large companies, they start with what it is readily available, right? So what it is off-the-shelf components, and because they want to have it into the data center. So this is if it is readily available and you can buy it immediately, this is one of the reasons to use GPUs. And when at some point it makes sense to have a custom architecture, then you proceed with a custom architecture with an ASIC or something like that, as it has been done in the past with, for example, that Microsoft, Google, for example, Google has these TPUs, right? Even Tesla, they have some custom chips that they have GPUs, but they also have some custom chips to train especially videos from the Tesla cars. So I guess the answer is that it depends on the scale. So you start with a GPU, and if you have the money and the budget, you can switch to an ASIC at some point.
I guess also the economies of scale mean that even though they're very expensive, you can generate GPUs on a larger scale in a way because they're so general, and then you can get the better contracts with TSMC, and you can kind of sell them more scalably. Like if you're a startup that's trying to build a bespoke ASIC for LLMs, you're operating at such a lower economies of scale that your product is going to have a premium, and it needs to be that much better to justify the premium over a GPU, which is already pretty good at this good stuff. So I guess it's very hard to enter the market. Even if fundamentally the technology is better, it's not general enough to get the economies of scale.
Yes, definitely. And the second thing is that the flexibility, because if you use GPUs or FPGAs, even if one researcher after, I don't know, 1 week finds out about a new algorithm that can
well, Mamba, like I wonder if they have all these ASICs for LLMs, like would Mamba work on them? Maybe not. It's quite different. So
yeah, the thing is that with an ASIC, if you decide, okay, I found a very good architecture for this large language model, so I will send it for fabrication. By the time that you will get the chip back, maybe there will be some new algorithms, some new implementation that it will provide even better speed up than the ASIC.
Things are also going very multimodal now as well. So obviously GPT-4 and GPT-5 needs to be able to do image generation, so it needs to be able to support stable diffusion as well, or something like this. And so you can't just have an LLM ASIC and it solved everything, I guess. I mean, what you could then end up having is like ASICs for each architecture, but I guess it's still early enough in the research that like it's still not clear that one architecture is won out. And I guess with ASICs, with hardware in general, like the cycle to build it is so long
Yes.
that you need to know years in advance that this is going to be relevant and it's going to be have a big market. And it's very hard to predict that in 5 years' time, everyone's going to be using transformers. Like it's very hard to make that bet confidently. So
exactly. What happened in the past, for example, it is the same story as in the case of communication, right? Once the protocol are it is not standardized yet.
Yeah.
You use FPGAs, etc. And once
Yeah.
you have a standard, a specific architecture, you have a specific standard for compression and encryption, then you move to a next. So I guess
makes sense. I guess what people are doing in the short term, obviously, is doing libraries because it's a lot easier to optimize a kernel than it is to create hardware that's scalable. So you have like TensorRT LLM, and there's like flash attention, and people are doing lots of clever stuff to push the current hardware as far as it can go because it's relatively low hanging fruit compared to designing a whole ASIC that is meant to have a big market, I guess. So I guess there's still things that can be done on the software side to push performance, and it makes sense to kind of explore that first as well. Because people still don't know if we've like fully tapped the potential of the current hardware just from software improvements and stuff, I suppose, is another thing. Yeah, interesting. Any other questions at all from the group? Any questions? I'm putting you on the spot. Do you have any thoughts or questions about that? You normally have a lot of opinions on hardware.
Yeah. So just like a quick question. You presented kind of the in-memory compute. I know that one of the drawbacks with that hardware architecture was that it was sensitive to noise and that kind of like digital and memory compute and stuff. So like, what are your thoughts on that? Do you kind of see that being relevant or like some other architecture popping up?
Yes, you are right. You're definitely right. But so this is the main disadvantage of this approach, and that's why we haven't seen a lot of in-memory computing paradigms, to prevail in the past for deep learning application or some other application. They are much more energy efficient, but as you said, they're very sensitive to noise because it is analog design, and analog design is hard to do. It's not as easy as it is digital design, right? So that's why I believe we haven't seen a lot of startups, or we haven't seen a lot of companies integrating in-memory architectures, right? Also for other applications.
Right. Yeah. Makes sense.
So I got a final question. Again, mine are all very open-ended, so not very specific. But I mean, based on your understanding of the hardware landscape, what would your bet be on the likelihood for companies to provide any meaningful competition to NVIDIA? Do you think NVIDIA pretty much own this market, or the vast majority of it for the next decade? Do you think there's going to be some real competition? If there is, how are they going to break in, given they have such a such inertia, and given that they have the economies of scale to their advantage already? Like, what's your thoughts on this?
Yeah, so I think only very few companies like Microsoft, Facebook, Google, etc., Tesla, etc., have the capacity to develop their own ASIC chips, right, in order to integrate it into the data centers.
Yeah.
The rest of the companies will be using NVIDIA or FPGAs because, for example, Intel has developed some very novel solution about FPGA accelerated AI. So especially in application when you need very low latency, FPGAs can prevail against GPUs. So especially for application like, for example, edge computing, FPGAs could in some cases provide better latency, and in some cases a better energy energy efficiency compared with the GPUs. But for especially for data centers, definitely NVIDIA will be the top.
That's kind of my feeling as well. There's a lot of interesting companies. There's like Tenstorrent, and there's I don't know, there's kind of obviously as Cerebrus and Salmon Systems and lots of these players. But you think your guess is that NVIDIA are going to keep an edge over all of the startups coming and trying to disrupt things?
Yeah, so there are some cases like in the past. For example, in the past, you see that companies like Nirvana or Habana Labs, they developed some very novel solution about the training and the inference part of AI. And this is why Intel acquired for several million or even billions in the case of Habana Labs, right? So maybe I don't know, but maybe there are some promising solutions in the domain of ASIC implementations. That I don't know if some of the researchers have a very novel solution and they can be the next acquisition from for Intel or someone if they develop a very novel solution and they manage to prove it into an ASIC.
Yeah. No, makes sense. No, yeah, I mean, we've been definitely impressed with the Gaudis and everything, and there's also interesting stuff with AWS and their training and inferentia and stuff as well. So I think there are like companies doing some interesting hardware stuff that then get snapped up by the big companies. Anyway, I could talk all day, but I'll close that. Any other questions from anybody at all in the room? No, we've got a round of applause online. We've got some watching on YouTube. So yeah, I don't know how you pronounce it, but Pro2on seems to enjoy it as well. So yeah, well, all of us in the room really enjoyed it. So thank you again very much, Chris. Really great to have you. We'll go check out your repository for sure and keep tabs on all the new papers that get added. We'll maybe make any PRs or issues if we find any ourselves as well. But yeah, let's stay in touch and hope you have a great rest of the day, Chris. And it was really a pleasure to have you with us.
Thank you for having me. Thank you for the invitation.
Of course. Thanks a lot. Bye for now, guys.
Thank you.
Bye-bye.